My name is Ramesh HG, Assistant Professor of Mathematics, Government First Aid College, Tiptur. Today I am going to explain some properties of subgroups with some examples. So let H is equal to 0 to 4 is a subgroup of G is equal to 0, 1, 2, 3, 4, 5 under modulo 6. You know that G is equal to 0, 1, 2, 3, 4, 5 is a group under addition modulo 6. Addition modulo 6. Because 1 plus 2 is 3, 3 plus 2 is 5, 3 plus 4 is 7, that is equal to 1, 3 plus 3 is 6, that is equal to 0, 4 plus 4 is 8, that is equal to 2, like this. So it satisfies all the properties of groups, and 1 is inverse of 5, 2 is inverse of 4, 3 is inverse of 3, 4 is inverse of 2, like this. It satisfies all the properties of group, and hence it is a group under addition modulo 6. So you consider a subset. You consider a subset of G, that is 0 to 4. You take the numbers 0 to 4. Verify the H for group. So clearly it also satisfies all the properties of group. So you observe that 2 plus 2 is 4, 4 plus 4 is 8, that is equal to 2, 2 plus 4 is 6, that is equal to 6, that is equal to 0. So it satisfies closure law, associative law, and 0 acts as identity element, and inverse of 2 is 4 and inverse of 4 is 2. Therefore this also forms a group structure, and hence this is a subgroup of G. So this is one subgroup of G under modular system. So H is equal to 0 to 4 is a subgroup of G is equal to 0, 1, 2, 3, 4, 5. So as H itself a group, and it satisfies all the properties, and hence it is called a subgroup of G. So you observe here in this table, so 0 plus 0 is 0 plus 0 is 0, 0 plus 2 is 2, 0 plus 4 is 4, 2 plus 0 is 0, 2, 2 plus 2 is 4, 2 plus 4 is 6, and it is equal to 0. This is 4, 2, and 4 plus 4 is 8, that is equal to 2. So it satisfies all the properties. Here all the elements of these are the elements of a group H, and inverse of 0 is 0, inverse of 2 is 4, inverse of 4 is 2. So it satisfies all the properties: closure, associative, identity, inverse, and also it satisfies commutative property, and therefore H is a subgroup of G. Next, this set H is equal to 1 minus 1 is a subgroup of G is equal to 1 minus 1 I minus I. So this is a group structure. G is equal to 1 minus 1 I minus I is a group structure under multiplication, is a group under multiplication. As it satisfies all the properties, so it satisfies closure property, and 1 is the identity element, and inverse of 1 is minus 1, inverse of minus 1 is inverse of 1 is 1, inverse of minus 1 is minus 1, inverse of I is minus I, inverse of minus I is I, and hence it satisfies inverse property, associative property, closure and identity, and hence it is a group structure. Suppose you take 1 minus 1 from this group, and let H is equal to 1 minus 1 is a subset of G, and this is also a group structure. It also satisfies the closure property, associative property, identity property, and inverse property. So 1 acts as identity element. Inverse of 1 is 1, inverse of minus 1 is minus 1, inverse of I is minus I, inverse of minus I is I. So H acts as this. It satisfies all the properties of group. Therefore, it is a group, and hence it is a subgroup of G. It's one of the another example. So let H is equal to 0, 3, 6 is a subgroup of G is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8 modulo 9. So clearly this is a group structure. and here 0 is the identity element of G. 0 is the identity element of G, and inverse of 1 is 8 because 8 plus 1 is 9, 0. Inverse of 2 is 7, 7 plus 2 is 0. Inverse of 3 is 6, 6 plus 3 is 9, that is equal to 0. Inverse of 4 is 5, and sum is 9, that is equal to 0. Inverse of 5 is 4, inverse of 6 is 3, inverse of 7 is 2, inverse of 8 is 1. So each and every element has its own inverse, hence it is a group structure. And hence it satisfies all the properties of group, closure, associative, identity, inverse. Then you consider H is equal to 0, 3, 6 from this G. So you observe that H also satisfy all the properties of group. Here 0 is the identity element of H. If you add 3 and 6, that is equal to 9, you put 0. Once again 3 plus 3 is 6, here 6. 6 plus 6 is 12, that is equal to 3. So it satisfies closure property. And 0 is the identity element. Inverse of 3 is 6, inverse of 6 is 3. And hence it forms a group structure. But H is a subset of G, therefore H is a subgroup of G is equal to 0 to 8 modulo addition modulo 9. So this is another example for subgroups. One more example. So you consider G is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 under addition modulo 10. So this is a group structure, modular groups. Here 0 is the identity element of G, and inverse of 1 is 9, inverse of 2 is 8, inverse of 3 is 7, inverse of 4 is 6, inverse of 5 is 4. 5 is self-inverse element. So each and every element has its own inverse, and hence it satisfies closure, associative, identity, and inverse elements. Therefore, it forms a group under addition modulo 10. If you take subset, two subsets here, two subsets. One is 0 and 5, another is 0, 2, 4, 6, 8. So these two forms a subgroup of G. As you see that in H is equal to 0, 5, 0 is the identity element, and 5 plus 5 is 10, that becomes the same 0. Inverse of 5 is 5. So therefore H satisfies all the properties of group G, all the properties of group, and hence it is a subgroup of G. You consider K, another set, another subset of G, 0, 2, 4, 6, 8. You observe that 0 is the identity element of K. 2 plus 2 is 4, 4 plus 4 is 8, 2 plus 4 is 6, and 4 plus 4 is 8, 8 plus 4 is 10, 10 is equal to 0, 8 plus 6 is 6 plus 4 is 10, that is equal to 0, 8 plus 4 is 12, that is equal to 2, like this. So it satisfies all the properties, closure property. And inverse is here, inverse of 2, inverse of 2 is 8, inverse of 6 is 4, and inverse of 4 is 6, inverse of 8 is 2. So each and every element of K has its own inverse, and hence K is a subgroup. So H and K are the two subgroups of G. Here G has two subgroups, H and K. H is equal to 0, 5, K is 0, 2, 4, 6, 8. So this is one of the beautiful example for subgroups. The set 0, 6, K is equal to, you take another example, the set 0, 6, K is 0, 4, 8, N is 0, 3, 6, 9, M is 0, 2, 4, 6, 8, 10. These are the subgroups of G is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 under addition modulo 12. These are the four subgroups of addition modulo 12. And here 0 acts as identity element. You observe that 6 plus 6 is 12, that is equal to 0. So inverse of 6 is 6, and hence H is a subgroup. You observe that 4 plus 4 is 8. 4 plus 4 is 8. So these are the 4 and 3, 6, 9. So these are the subgroups of G is equal to 0 to 11 modulo 12. So let one theorem, the intersection of two subgroups is also a subgroup. So it is one of the important property of subgroup. Intersection of two subgroups is also a subgroup. Let H and K are two subgroups of G. Let H and K are two subgroups of G star. That means H satisfies all the properties of group, K satisfies all the properties of group. Then we have to show that H intersection is a subgroup of G. Let A comma B belongs to H intersection K, A comma B belongs to H intersection K, then A comma B belongs to H and A comma B belongs to K. A comma B belongs to H, then AB inverse. So this is AB inverse. AB inverse belongs to H and A comma B belongs to H, then AB inverse belongs to K. So AB inverse belongs to H. AB inverse belongs to H intersection K. Hence H intersection K is a subgroup of G. So for this, for example, you take any example, H and K are two subgroups, and you have to show that H intersection K is also a subgroup of G. But the union of two subgroups need not be a subgroup. Union of two subgroups need not be a subgroup. If you take set of all integers, then 2z and 3z are two subgroups of z. So let z be the set of all integers, and it is a group under addition. If you take 2z and 3z are the two subgroups of z, you take the intersection 2z intersection 3z, so we get 0 element, and that is clearly a subgroup of G. But if you take union, so it contains 2z union 3z. It contains 2 belongs to 2 and 3 belongs to 2z union 3z, but their sum is 2 plus 3 is 5. So 5 is not in 2z union 3z, and hence it is not a group structure because it does not satisfy closure property. As you know, 2z contains all multiples of 2, 3z contains all multiples of 3, but 2z union 3z contains all multiples of 2 and multiples of 3. But 2 comma 3 belongs to 2z union 3z, but their sum is 2 plus 3, that is 5. It is not present in the 2z union 3z, and hence it does not satisfy closure property. Therefore, it is not a group under addition. So union need not be a group, but the intersection of two subgroups is a subgroup. Union need not be a subgroup. So up to this we have studied what are subgroups, what are its properties, and some examples. So a subgroup H is a subgroup of G if and only if it satisfies all the properties of group: closure, associative, identity, inverse, and commutative property. If your commutative property satisfies, it's called as an abelian group. So examples, so many examples I have already given. So 1 minus 1 is a subgroup of G is equal to 1 minus 1 I minus I, and 1 is the identity element. Minus 1, inverse of minus 1 is minus 1, and inverse of 1 is 1. So similarly 2z, 3z, 5z, 4z, these are all subgroups of a group of integers. And you come to theorem, intersection of two subgroups is a subgroup, but union need not be a subgroup. Thank you.